This is the 11th video of the series Business Forecasting, and in this video we will discuss multiple linear regression. So unlike the simple linear regression, which has only one predictor variable, like x is the only one predictor variable for simple linear regression, in case of multiple linear regression there can be multiple predictor variable like x1 x2 up to xn, and you can recognize these are the regression equation for the population, and the corresponding sample regression equations are this one. So b0 and b1 are the intercept and slope for the simple linear regression, and correspondingly b0, b1, b2, b3, this b1, b2, b3, these are the slope coefficients for the multiple linear regression, and like b1 is the slope for x1, b2 is for x2, and so on. So in this way multiple regressions are defined. So now we will directly go to our SPSS software and solve one problem there. We will take out one regression output, multiple regression output, and then we will discuss. So let us move on to the SPSS worksheet. So this is our problem. See here, 67 products are given here, and for all these products the calorie count, sodium amount, fiber amount, carbohydrate, and sugar, these are noted here. So first of all, identify here that this data is not a time series data. Why? Because 67 products have been taken, and most probably they are taken in a single point in time. So this data will not vary as per the time. In a particular point in time, all the 67 data points have been taken. And what is the dependent variable here? Dependent variable or the response variable is the calorie, and the independent variable or the predictors are these four: sodium, fiber, carbohydrate, and sugar. So as usual, you need to fill up the variable view also. Just you need to change these names. By default they will be variable 1, variable 2, and so on. You just need to type out this product, calorie, sodium, etc. here, and make sure that the product is nominal. I have kept it a categorical variable because this is not required here, and rest all are scalar. That means product is an attribute and these are the variable data. These 5 are the variable data. So anyway, this is that input here. And so how to perform the regression? Go to analyze and then regression, and then regression, then linear. Once you go there, the dependent variable is calorie, so select calorie here and then enter from here, and then independent variables are sodium, then fiber, then carbohydrate, and then sugar. Once you entered this, go to the statistics. Here click on collinearity analysis and this Darwin-Watson. Okay, these two are checked in, and then continue. Nothing else is actually required here. You can take out the standardized residual plot. So SRE SID goes to Y, and in X dependent variable goes to X, and you can take out the histogram and normal probability plot also. All this is done, and then you click on OK. These are the outputs. As usual, you know that there are three parts in the output. One is your model summary, one is your ANOVA, and the last one is your coefficients. So three types of outputs are there. So we will discuss one by one, but let us come to the slides once again. So this is the first part, that is the model summary. Here you get to see the R square value and the adjusted R square value. So first of all, note that when we are dealing with multiple linear regression, we should never go for only the simple R square value. In case of R square value, we should refer to the adjusted R square value. And why so? Because if you just include any independent variable, additional independent variable, which is not even related to the model, completely unrelated, irrelevant independent variable, then also your R square value will tend to increase in case of multiple linear regression. So that kind of bias can be removed using adjusted R square value. So you don't have to believe me, just experiment. Just again go to the SPSS worksheet. So this was my worksheet. I have taken out these 67 random numbers. These are completely random numbers. The numbers are generated using Excel between 0 to 50. I will copy these numbers here. So basically I am creating another variable which does not have any meaning, just another variable of random numbers. I will give a name bogus, because this is a bogus variable, nothing to do with the model or the data. Now please note the values of the R square and adjusted R square in the previous model. This was 0.742 and this was 0.728. I will take a snapshot. This is a snapshot I have taken. Okay, let it be minimized here, and then I will go to regression, linear, and now I will add the bogus variable here in the independent variable. Then we'll do nothing, just click on OK. So a new output will be populated, and this is the new output. You see they have included the bogus variable here. And what is your R square value now? This is your R square value, 0.744. So earlier it was 0.742. Now it is 0.744. So see, just I have included one bogus variable of random numbers. Still the R square is improved for nothing. But if you look at the adjusted R square value, it was 0.726 earlier, but now it has come down to 0.723. So adjusted R square value is trying to rectify that, or at least not inflating the value. So this is the protection you get if you use the adjusted R square value. If you are quite sure that these variables that you have taken are related to the model or actually explains the dependent variable, then you may use the R square value also. But suppose you don't have any idea about the independent variables or their relationship with the dependent variable, then it is always better to refer the adjusted R square value. So now since we have experimented this, let us come to the slide once again. So the next point that is new to this model summary compared to the simple linear regression is the Darwin-Watson statistic. So what is that? The statistic will give you the idea about one period lag autocorrelation of the residuals. So what is autocorrelation and what is one period lag? I have discussed these things in my second video in this business forecasting series. So if you want to see that, so check out that video, you will get to know. But just very briefly, autocorrelation shows you whether there is a trend in the data. So if there is no autocorrelation is 0 or very low, that means that the data is not trending, it is a stationary data. So we want that the residual should be stationary, not trending, and therefore the autocorrelation should be minimum. And Darwin-Watson statistic gives us the measure of autocorrelation. And what is the criteria? Basically, ideally tables of Darwin-Watson should be used, but if you don't want to use the tables, just remember that 1.5 to 2 value is okay, sufficiently okay, but anything less than 1 or anything greater than 3 is bad, is not to be used. The model should be revised. So these are the parameters that need to be covered in the model summary part. And so what is the next part? Next part is the ANOVA, you know very well. So in the ANOVA, first of all, we check the significance value, that is the p-value of ANOVA. And what is the hypothesis? We have already discussed this thing, but in this case, the hypothesis is little bit different from the simple linear regression. What is the null hypothesis? Null hypothesis says that all the beta slope coefficient, population slope coefficients are equal to 0. And what is the alternate? Alternate is at least one of these beta values, at least one of these beta values are different from 0. So it does not say which one. That means any of these, just one of these can be different from 0. That is okay. So that much is checked. So what is the conclusion then? Conclusion is, if you have p-value less than 0.05, then at a 5% significance level you reject the null hypothesis. And what does you conclude by rejecting the null hypothesis? You conclude that the linear model is overall significant. So if you reject this one, that means you are going with this HA. Rejecting H0 means you are going with HA. HA means at least one of the BI values are different from 0. So if one of the BI values are different from 0, that means your linear model that you proposed, that is mu y is equal to beta 0 plus beta 1x plus beta 2x2 and so on. So at least one is different from 0 means you have a linear model. So that means the linear model that you have assumed is overall significant. That is the significance of ANOVA here. So in this model also you have a significance value less than 0.05, that is 0.000 here. So that means a linear model is good to go with this data. And then what is the third part? Third part is the coefficients part. So you first of all you have to note the coefficients. So these are the coefficients. First one is 21.891, that is your constant or your intercept. This is the intercept value, and these are the slope coefficients. Which slope coefficients are these? These are the sample slope coefficients. So if you want to write the regression equation, it will be like this. So first of all, this is 0.024, 0.659, 3.433 and 3.941. So just in this order. And this is your sodium quantity, fiber quantity, carbohydrate quantity and sugar quantity. Now what else to see here? The second point that you need to note here is the p-value of the individual coefficients. Earlier in ANOVA we discussed about the entirety of the model. That means whether the overall model is significant or not. In this case, in the coefficient section, we will see whether each individual coefficient, that is beta 1, beta 2, beta 3, whether they are significant or not. So see here, I have written down all. So for example, the sodium variable, what is the hypothesis? So this is the hypothesis. Null hypothesis is beta 1 is equal to 0. Alternate hypothesis is beta 1 is not equal to 0. And what is your p-value? P-value is 0.140. This one. This is greater than your 0.05. So therefore you cannot reject null hypothesis. So this null hypothesis cannot be rejected. So remember the rule, whenever your p-value is less than 0.05, you will reject null hypothesis. And if your p-value is greater than 0.05, you fail to reject null hypothesis. So what happens here? Your p-value is greater than 0.05. So according to this rule, you fail to reject the null hypothesis. So what was the null hypothesis? Null hypothesis was beta 1 is equal to 0. So therefore, the slope coefficient is really not different from 0 in the population. And similar observation is true for fiber also. Here also you see p-value is greater than 0.05 and hence this H0 cannot be rejected. So beta 2 equal to 0, this cannot be rejected. That means the slope coefficient is really not different from 0. But for the next two, that is carbohydrate and sugar, you can see the p-values are less than 0.05. Check here, these two are less than 0.05. That means you can reject this one and go with this one, go with this one. So beta 3 and beta 4 are significantly different from 0. That means the slope you got here 3.433 and 3.941, these two can be safely included in the model. So then what to do? You have found here that these two slopes, this one and this one, these are insignificant, not really different from 0, and also found that these two are significant. That means these values are good to be included in the model. So one option here is just drop these variables. Drop means just replace these by 0, 0. So basically that means you just drop these two variables. So what remains is yu is equal to 21.891 plus 3.433 into carbs plus 3.941 into sugar. So one option is this, but this is a naive option. What we actually do here is we perform a stepwise regression procedure that we will also do using SPSS. So let us come to the SPSS worksheet once again. So in this case you have to go analyze regression linear. There is no difference up to this. I will just remove this bogus variable from here and then check here. There is something called method. By default it will be enter here. Enter means basically all models included. So we had all independent variables included. We had 4 independent variables here. So if you select the enter, you don't have to select, it is already in default here. So the model generated will include all the models. But since we have seen that using the p-value method, the two of these independent variables are not significant, so we are using the stepwise method. So using this drop down, select the stepwise and then again click on OK. So let me give you a brief introduction. What does this method does here? Basically the stepwise method takes the independent variables one by one and performs the ANOVA, and if the ANOVA is significant then it keeps that variable, and if the ANOVA is insignificant it removes that variable. So using that method it works, and using that method it has proposed you two models, 1 and 2. In the first model, see this A and B here. Under A they have used just one predictor, sugar, and under B they have used sugar and carbs, two predictors, and dependent variable is obviously calories. So you see here using stepwise regression they have already removed our two variables that were found insignificant in the earlier model. Which were those variables? Those variables were your fiber and sodium. These two variables were insignificant, and the stepwise model has removed these two variables, but it has proposed you two models. So model 1 and model 2. Model 1 contains just sugar, independent variable, and model 2 contains sugar and carbohydrate. So which one we will select? Very simply you will select that one which had the higher r square value or adjusted r square value. You see very clearly model 2 has your better r square value, that is 0.726 or 0.717 adjusted r square value. So you will always select model 2 in this case. So let us come to slide once again to continue the discussion. So this was your stepwise regression output. You can see clearly here we are selecting model 2 because we will not select a model having poor r square value. We will select that one which has a higher r square value or adjusted r square value, and therefore we are selecting this model, sugar carbs model. And for that model new set of coefficients have been proposed. Significance value is also there. So what will be your equation? Equation is 28.760, this one, then 3.906, this one, 3.358, this one. So this is your final model. And your Durbin-Watson statistics is also okay. This is less than 2. This is perfectly fine. Another thing that we need to discuss here is the variance inflation factor, VIF. VIF stands for variance inflation factor. Why we should discuss that? Sometimes it may so happen that you have selected independent variables, that is fine, more than one independent variables are there, but these independent variables can be themselves interrelated or intercorrelated. For example, if you have a model of say multiple linear regression, some kind of dependent variable that takes both height and weight of human beings. So now you see mostly height and weight are interrelated. So somebody, if he is too tall, maybe he will be having higher weight, and a person who is not so tall will have lower weight. So this height and weight, although they are two independent variables, they may be correlated. So then there is no point in taking these two variables together. Unnecessarily one variable will try to inflate your r square value for no reason. So we need to separate out one variable. So but in that case we have to make sure that these two variables are correlated. So your VIF value gives you that measure, that whether these two variables are correlated or not. So what is the standard? The standard is VIF should be close to 1, and which is very ideal. It never happens, and anything below 2.5 is good. Sometimes it is 3 to 4 is also good. Too high value like 7 to 8 or 5, 6, 7, 8, if the VIF value is in this range, then you should think about it. Otherwise, for 1, 2 and 2.5, this type of values are acceptable for VIF. So this is all about multiple linear regression and the analysis of the output. Hope you have understood everything here. I have tried to cover every aspect of this, and theoretically this is all. Just we will revise the chart output also in the SPSS. So let us come to the SPSS again. So these are the chart outputs. You can see here, this is the histogram of the standardized residual. It looks like it is following a normal distribution, and this is also clear from the PP plot. These residuals, this point should be following the straight line for a normality, and they are following as it seems here. So the residuals seem to be normally distributed, and they should be, the standard residuals should be distributed equally around the zero line, both above and below. So looking at this, I think few points are really towards the above side, like more points, maybe I am wrong, or it may be equally distributed. So more or less equally distributed, so the model is not so biased. So that is all regarding the theoretical discussion of the multiple regression output analysis. I have discussed the output and the graphs as well. Hope you have understood, and in the next video we will see how to leverage multiple linear regression in case of time series analysis. So again note that this video was regarding multiple linear regression, but we have not used any time series data. That data was a cross-sectional data, but we can use this concept in time series also in analyzing the seasonal variation. So that we will see in the next video. But until then, goodbye and thanks for watching this video.